Hi, this is the fifth and last Physics 2212 lab magnetic molasses. Okay, so the purpose of this lab is to collect observational data of a magnet falling through a conductive tube of aluminum foil, simulate the interaction in GlowScript, and to compare the measured data to the simulated data. And what we found in this lab is that the actual average time for the magnet to fall through the tube was 1.49 seconds, and the time we found from our simulated GlowScript model was 1.118 seconds. So our results from the model were very close to our experimental results. And so here's some background information that we need for this lab. There's Faraday's law, which is the line integral of the electric field, otherwise written as the negative derivative of flux with respect to time. Additionally, the magnetic flux is calculated as the integral of B dot A, or more simply, the magnitude of B times A. And in this lab, we're going to use the specific definition of the derivative of flux as shown here. Furthermore, the magnetic force on a wire is calculated as IL cross B, and the force or on a wire loop is 2 pi r times IB sine theta. Ohm's law is V over R, where V is the negative derivative of flux with respect to time. So the experiment went something like what I have drawn here, where we dropped a bar magnet through a ring of aluminum foil. And so we positioned the magnet with the north side down so that mu would point straight down. And what happened was a counterclockwise current was induced to counteract the mu of this bar magnet, since the whole system wanted to generate a B that would resist the change in flux. And so we got our experimental results by taking 5 separate videos of myself dropping a magnet through this aluminum loop. And I went back through the videos with a stopwatch and recorded when I dropped the magnet and when I saw it come out of the loop. And so, of course, there was probably human error in my data from this approach because the times were heavily dependent on my reaction time. And for the computational model, we used GlowScript. We first initialized all of our constants as well as the graph. Here we initialized some more important numerical parameters and created the aluminum tube and created the bar magnet. And after this, we defined the functions for both a magnetic field due to the dipole or the magnet, and we created a function for the magnetic flux created by the bar magnet. We then calculated the gravitational force on the magnet and the magnetic flux on a ring due to the magnet. And using this, we then calculated the current through the aluminum tube. We then calculated the magnetic force of the falling magnet on the aluminum tube and then the magnetic force of the aluminum tube on the magnet using Newton's third law. We finally were able to calculate the net force by adding the gravitational force to the magnetic force using superposition, and the changing velocity and position of the magnet were calculated using Newton's second law. A graph was created to demonstrate the change in velocity as a function of time. And these are the results. On the left, we can see the magnet as it's falling through the tube. You can see that the induced magnetic field on the bottom is opposite the induced magnetic field on the top. We can also see that initially the velocity is decreasing, and it increases once it hits the tube, stays constant throughout the tube, and decreases once more once it falls out the tube. And the time in the tube calculated from the model is 1.118 seconds. Okay, so what if resistivity were reduced to almost zero? And this would make it so that the induced current could be much higher, and thus the induced magnetic field would be much higher, so the magnet would fall much, much slower, almost to zero velocity. And what if holes or slots are cut into the tube? And this would interrupt the currents and we would see no effect at all. In fact, the magnet would just fall through the tube as if the tube weren't there. All right, that is all I have for today. Thanks for watching.